Hi, everyone. This is our last video for Chapter 10. We're going to talk about rotational work and rotational power. So we want to talk about the linear experience to suggest equations for work with respect to torque. So we have work, right? Work is the force times distance traveled times cosine theta, right? This is also the same as saying this is the integral of force with respect to the displacement, right? So that's what we have linearly. Now, rotational work, okay? We remember that we've always said that torque was kind of like angular force. So that's going to work here as well. So this starts with the idea that the integral of torque with respect to the angular position, right? As angular position changes, we're going to analyze how the torque is changing, right? So that leads to us saying that torque delta theta is our equation for for rotational work. Now here you can see that there is a difference, right? Here cosine theta is in the equation for work, but here there is no trig for the equation for rotational work. And that is because your trig is in torque, because torque is Fr sine theta, right? So that is already built in. So there is trig in it. Don't think that you're off the hook yet, but there is trig. It's just already in torque, so you don't have to. And there is no, torque delta theta cosine, and then you think that you've got cosine and sine, then you're going to have some kind of tangent nonsense. No, the sine is in the torque, so you don't have to worry about having more trig with your work. Now, we also have the work kinetic energy theorem, right? So the work kinetic energy theorem is the idea that the work on a system is equal to the change in kinetic energy, which would be K final minus K initial, right? However, here we're going to use rotational kinetic energy to show that 1/2 I omega final squared minus 1/2 I omega initial squared. That's our new equation, right? All we did is substitute rotational kinetic energy for linear kinetic energy, but it works just as easy, works in the exact same way. Now we had the power equations, right? Power, average power, right, was the change in work over some time, right? Now, we also had instantaneous power, right? Instantaneous power was the integral of work. No, sorry, that was the derivative, not the integral. That was the derivative. So we have dw over dt, right? Now, this delta w, delta t, this does not change. What changes is here, right? It is still changing work over time. It's just that now we're looking at a different kind of work, right? The only thing that might change here is that now you put an R on it, and that's all that will change for that. Now, for dw dt, right, that is now the derivative with respect to time of torque, torque times delta omega, right? So we don't want to put that derivative with torque, but if we put it with the theta, we could say that this is torque times the derivative of theta with respect to time, which is just torque omega. So remember that d dt, when you're doing your calculus, sometimes that can be pulled out and moved wherever you need it. And this is a very convenient spot to put it. So we're going to leave it there and call that torque omega for instantaneous power. And if you remember, for linear power, for instantaneous, we had force times velocity. So you can see here, angular velocity, and what we're going to consider angular force. Right? So these are the equations that we are going to work with through 3 practice problems. Now, first we have a grindstone, right? A constant torque of 25 Newton meters is applied to a grindstone. Write this as we go. Newton meters. A grindstone with a moment of inertia of 0.130 kilogram meters squared. What we're going to do first is use energy approach to find the angular speed after 15 revolutions. Okay, so delta theta is 15 revs. Then it asks, would the instantaneous power be constant in this situation? So we'll answer that question. Part C, what additional data do you need to calculate average power? So we'll talk about what we need to find average power, and answer what is the instantaneous power at the end of the 15 revolutions. So let's start first with the energy approach, right? I am going to change, my iPad's not playing ball. Delta theta, okay, 15 revolutions. I want that as 30 pi, right? We get that from 15 revolutions, and then every revolution is 2 pi radians, right? So I want that in terms of radians so that we can get our math all squared away. Now we've got our torque is 25 Newton meters. Our moment of inertia is 0.13 kilogram meters squared. Now we're going to use, it's said to use an energy approach. So we will use an energy approach to find the angular speed. What we'll do is we will say that the change in kinetic energy is equal to the work on the system, which is equal to torque times, no, not omega, torque times theta, right? So our delta theta is 30. So we have omega naught would be 0, right? It is starting at rest. So we have 1/2 I omega final squared. That would be -0, so I'm not going to write that, equals torque times our delta theta. And we want omega final, right? So let's solve for omega final. Omega final squared, I won't put the square. We will have 2 times torque delta theta divided by your moment of inertia, all under a square root, right? Multiply 2 to get rid of that 1/2, divide the I, square root it. Okay. That means that we will get, for our omega final, the square root of 2 times 25 times 30 pi, all divided by 0.13. Okay. And you should get approximately 190 inverse seconds, or radians per second. Right? Just remember, don't write the radians. So that's what you get for your omega final after 15 revolutions of that constant torque being applied. Now, next question asks, would the instantaneous power be constant in this situation? Well, let's talk about what we have for instantaneous power, right? Instantaneous power being torque times omega. Here, if we had instantaneous power, right? Torque is constant, but the omega is not constant. Okay? Since that is constantly changing, the instantaneous power would also constantly be changing. Now, letter C says, what additional data do you need to calculate average power? Well, let's look back. Average power would be delta W over delta T. So if we wanted average power, we would have, we know the change in work, right? But how long did it take, right? We don't have the time on this problem. Now we could probably get it, right? If we look at our angular kinematic equations, let's see, we've got a couple. We have omega final equals omega naught plus alpha t. Then we have theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And then we also have omega final squared equals omega naught squared plus 2 alpha delta theta. So I would not use that second one. That looks overly complicated for what we're trying to do. Way too many unknowns on that one. You've got a time that we're trying to find is squared and everything, so we're not going to do that. But here we don't have alpha. So what we could do is use this. That's 0, right? Same there, that's 0. So we could use this to find our alpha, then put it into that equation. So let's do that real quick. It shouldn't take too long. Let's see, alpha down here will equal omega final squared divided by 2 delta theta, right? All right, so we have, what is it, 190 was our omega. So we have 190 squared divided by 2 times 30 pi. So let's see what we get for that. So I got 191.5. Okay, so this is going to take about a second. 191, yeah, 191.5 to the seconds to the -2 power. So if we put that up here, time will equal omega final divided by our alpha. This is going to be really close to 1 second, right? You've got 190 divided by 191.5. Yeah, that's 0.992. 0.992 seconds, so almost 1 second. So our average time here would be, what is our change in work? So that would be 1/2 I omega squared over 0.992. So let's see, we got 1/2. Do we have the moment of inertia? We do. 0.13. Omega came out to be 190 divided by 0.992. Let's see what we get. 12.45. 12.45 watts. Okay, so that would be our average power over that period of time, right? So we can find that. Now, number 4, or I guess letter D, asks what is the instantaneous power at the end of those 15 revolutions? So let's find that. Instantaneous power at the end of those 15 seconds. That would take the torque times omega final at 15. So you've got 25 times 190. That comes out to 4,750. 4,750 watts. That leads me to believe that that average power may not be correct. So that's interesting. I'll have to look over that. I figured out what I did wrong. I did not square my 190. So let's redo that. If I square the 190, then divided by 0.992, get 2365. Much better. So that was the issue. Don't forget your squares. So that looks a little bit better. Average is, from our experiences in this class, kind of close to half. Okay, it's going to be in the ballpark of half of your instantaneous power at the end of your time period. All right, and that was all of our stuff for that problem. Let's go to the next one. So now we have flywheel energy in rotational world. So a flywheel is a part in a car. Flywheel is a solid disc. It's got a diameter of 0.6 meters. So that means a radius of 0.3 meters and a mass of 200 kilograms. That is mounted on a frictionless bearing. Motor connected to the wheel accelerates it from rest to 1,000 revolutions per minute. Now, I'll give you guys a hint. That is 104.72. That is in radians per second. Okay. Now, how much work is done on the flywheel during that acceleration and at 1,000 revolutions per minute? The motor is then disengaged and a friction brake is used to slow the rotation to 500 revolutions per minute. How much energy is dissipated by heat by the brake? So we will use conservation of energy for that one as well. So how much work is done by the flywheel during this acceleration? So what we're going to do first to find work, right? Work will be 1/2 I omega squared, because we can say omega naught is 0, right? So it's going to be equal to the final kinetic energy. Our I, okay, this is a solid wheel, right? So you've got mr squared over, not r, mr squared over 2. So you've got 1/4 mr squared times omega final squared. So you've got 1/4, our mass is 200, then our radius 0.3 squared, and our omega 104.72. Square that. Lots of squares in there. Don't forget those. That comes out to approximately 49 kilonewton meters, about 49,000 newton meters. Or 49 kilonewton meters. So that is the approximate. I got 49,348.25. So if you got something really close to that, we're on the same page. Now that's the work done, right? We just use work kinetic energy theorem. Now at that speed, it suddenly engages a brake. So here we're talking friction, right? Energy loss due to friction. So let's see. We're going to have new initials and finals. So omega initial is now 104.72, right? And now our omega final is 500. Not 500. Yeah, 500 revolutions per minute. Okay. Now that is going to come out to be 52.36 inverse seconds. Just divide the 1 by 2, right? So that'll get that done there. So now we can set up our COE. Okay, it is moving with an initial kinetic rotational energy. It ends with a final rotational kinetic energy, and it's maintaining that 500, I assume, right? Yeah, slows it down to 500 revolutions per minute. Now, to find the energy dissipated by heat, we're assuming that all of the friction dissipates as heat, right? That energy has to go somewhere in a flywheel, in a motor. When you're just pushing on something to slow it down, that energy is lost as heat. Now, it might be absorbed by the air or by the brake. That's not what we're looking for, right? We're just looking for what is the work due to friction, right? So we will have Kr initial minus Kr final, and that will equal our work of friction. So our initial kinetic energy, 1/2 I omega initial squared minus 1/2 I omega final squared. So let's go ahead and put this in. We've got 1/2. I'll just skip that 1/4, right? Our moment of inertia is a half. So we got 1/4 m r squared times omega naught squared. I'm even going to take a shortcut here. Since you have 1/2 I on both of them, 1/2 I doesn't change. So then you just have omega naught squared minus omega final squared. Let's see, that would be 1/4 times 200 times 0.3. Oops. Uh-oh. Times, was it 104.72 squared minus, is it 52.36? 52.36 squared. And that will equal our work due to friction that is dissipating as heat. and I got about 37,000 joules, or 37 kilojoules. I got 37,011.2. So if you're on that, in that area, you're good. So that is our A and that is our B, right? That is the energy dissipated as heat by the break. Now, this last one is pretty tough. So we're going to, this is linear work and angular world. Sometimes you don't use angular work or rotational work. Excuse me, sometimes you have to use linear work. So we have a top over to the right, spun on the axis A prime, and it has a moment of inertia of 4 times 10 to the negative fourth. Oh, that's small. 4 times 10 to the negative fourth kilogram meters squared. If the top is pulled with a constant tension force of 5.57 newtons, what is the angular speed after 80 centimeters of string has been pulled? That's interesting. So this is why we're going to have to use linear work. Okay, so we could look at, right, an arc, right? You've got angle theta, arc length S, radius R. We could try to figure out what is the theta here, right? Delta theta should be delta S over R. Okay. However, we don't have the radius. We don't know what the radius is, so this is going to make that impossible. So what we're going to have to do is settle for an equation that uses delta S. So how we can do that? Okay, our linear work. Okay, linear work is force times some displacement. But here, that displacement, we can say is that arc length, right? Because that's the true displacement of the force, right, that's being exerted. So it is exerted over 80 centimeters. So we could say that delta S is 0.8 meters. That also finishes off with a cosine theta, but it is tangential to the rotation, right? Or I guess the force and the displacement are actually in the same direction. So if the arc length is our displacement, the rope for the force is also wrapped around the arc length, so that cosine theta will become 1 and negligible. So now the work would be 5.57 newtons times 0.8 meters. Okay, so that'll give us 4.456 newton meters. Now that was not what it asked us though, right? It wants the angular speed. However, work can equal the change in kinetic energy. Now, just because we found the work using linear methods doesn't mean that this can't equal 1/2 I omega squared, right? I'm going to unbox that. I shouldn't box it if it's not the right answer. Circle it. So just because we use linear work doesn't mean that it can't also use the angular kinetic energy theorem, right? Work kinetic energy theorem. So we will break down this kinetic energy to get our omega, right? We're looking for omega. Yeah, so we will just solve for omega here. To find omega, you multiply that 2 over, so you got 2 times the work, divide by your moment of inertia, which we were given, and then we will square root it to get that omega final. Whoops, that's not squared though. So you have the square root of 2 times 4.456, and that is all divided by 0.0004, right? 2, 3, 4, yep. So that's going to be a big number, right? What I got out of that is about 150. Okay, I actually got 149.265. But we certainly don't have that many sig figs in this problem. So I would actually cut that down to 149 radians per second. Right? But that's just to introduce the idea that you can use linear work and angular work interchangeably. It just depends on what you have, right? The work done on an object, it doesn't matter how you found that work, right? The work done on the object is the work done on the object. It just depends on what you can use to find that work, right? All right. That wraps up our video on rotational work and power, and that's actually our last video for chapter 10. And in our next chapter, we're going to start exploring angular momentum.